I would like to dig a little more into our, what we call our accumulation framework, where we accumulate these different local visual feature descriptors. So we've not done any global or linking of features yet. It's purely local basis, and we do everything here in 3D. The idea is to get rid of outliers. You see, this is a typical image, it's a bit dark, of a robot holding an object. This is the 2D representation with line segments. And after matching and reconstruction, you see a lot of outliers and also noise in the extractions. So what can we do to build up a more complete and reliable model of this object? We rotate the object using the robot. Oops. And try to use this temporal information to get a better model. Again, these are our features we can use in this framework and the associated parameterization. I think I'll just go over that. We have talked about that. So to test this, we create an artificial object using OpenGL and introduce some noise, because there are always noise in our images. And then we extract 2D features. Here we visualize the matching required to compute the 3D. So from the left and right features we match. See if we can find the matching feature, and you see we don't change the viewpoint too much between the two cameras to not make it too difficult to do this matching. And these lines indicate from the left image where we found the best match in the right image. So they are all horizontal according to the epipolar line. Doing the reconstruction, we get these 3D line segments. You'll notice that this line is completely missing, as well as this line. And why is that? Well, from the input image, we see that these lines are almost horizontal. And matching a line that is horizontal is very difficult, because the only constraint we have, or the most powerful constraint we have, is the epipolar line. So we are searching along the line, and they all look the same. So we have a lower bound of angle. So if it's too close to horizontal, we can't extract the line segments. That's why these are completely missing. But rotating the object, we will at some point extract them and put them into our accumulated model. We also introduce the junctions and textlets. So going from this line segment-based representation to this, when we visualize junctions using green dots and a few textlets in this textured surface of the cube. The accumulation framework, in short, looking at it as an algorithm, is generic, so we can use all these features if they just implement basic methods. And we use it for temporal disambiguation, meaning, yes, we want to remove the outliers and get more robust. The algorithm is looking like this. First, we have a prediction step. It's basic Kalman filtering. We have to have a method for predicting, okay, having the scene representation in one image, where do we expect it to be after the motion we apply in the next image, in the next frame. If the camera is moving or the object is moving, it doesn't really matter. We just have to know the relative motion. Then we need a method for matching the predicted representation with the observed. And at this level we match on the feature level. So each feature has its own Kalman filter associated, and so we try to match each feature with all features in the other frame, in the newly extracted or observed scene. Having found matches, we correct our representation using an uncensored Kalman filter. This means that we need to have an uncertainty associated to all of our features. So we do that during extraction. We compute an uncertainty for all our parameters, and then we use an uncensored Kalman filter because of our parameters being highly, or our function, our transformation being highly nonlinear. Finally, we have a probabilistic step where we update the confidence of each feature. So how, depending on the quality of the match, how confident are we that this is actually a line segment that is representing something in the physical world. Yes. Some formalism. We have our parameterization now in a bit more detail. We have the geometric parameters, the appearance, and the associated uncertainties as a covariance matrix, and the belief associated to each of our features. Features being either homogeneous patches, an edge, a line segment, junction or textures. And then we, for each feature, need to implement this, so to speak. This is the position, pose, basically the geometric information, how we update that over time during rigid body motion. And here, for simplicity, we assume for now that appearance stays constant. This is not necessarily true, but we use that simplification. Rigid body motions are computed using dual quaternions, and because of this, there's no analytic approach to transform our uncertainties. That's why we use the uncensored transform, which is basically a Monte Carlo-like approach. I don't know how much I should go into detail with this, but it's a method of, if you have the uncertainty in one frame, how you can propagate that to the next frame through your function simply by selecting a minimum set of sample points and doing some statistics on where they end up in the next frame. That will give you a new uncertainty. The second step is our matching. We have a weighted matching depending on the uncertainty. So where we are sure, we have a higher weighting. And as I try to visualize here, if we have multiple possible matches, then in this framework we can actually store both of them. And then after having predicted, we can easily see, okay, this one down here, so this represents two different possible matches. And in the next frame, after having done the prediction, we see that, okay, this one fits, has a match, and this one has no good match. So we can do disambiguation over time in this way. Our correction step is basic Kalman filtering. Having the uncertainties, we just apply the normal steps. And our confidence update, we have some prior probabilities of a correctly and erroneously extracted features, of course some estimates, and using that we can, depending on the matching history, compute our next confidence. And yeah, you just more important is that we have also newly extracted matches. They get into the representation if they're not matched with the initial confidence, and then we have mechanisms for discarding primitives if the confidence gets too low. We'll just remove them from the representation. If they fail to match for long enough, then they were probably just an outlier. And on the other side, we have a mechanism for freezing the primitives. You know that at some point it might be occluded, and because of that, we have to freeze primitives if the confidence gets high enough. Over a couple of frames, then we freeze it, so we will never remove it. We will keep correcting it, but if we fail to match it, we won't remove it or lower its confidence. Next question.
The initial confidence, do you have any way of deciding that, or is just?
I didn't do this work, but I think they did some testing on. Okay, can we actually see? Of course, it depends on so many things. So in the end, it's a guess. It depends on the noise and what you actually want to see, because it's the noise in your image. So if you look at textured things, they might be actually correct, but yeah, where's the limits? So I think we use 20% chance of correct extraction. Yes. Right. So I use this artificial object for testing, because then I know the geometry of this. I know the exact camera parameters from the OpenGL generation. And after one iteration, my representation looks like this. And I look now from the other side of the object into the object. You see, it's a somewhat sparse textured surface, and some of the corners are missing. Also, you see this line. Okay, looking at it from this angle, this viewpoint, is actually okay, but that's just because it's the same as the camera, or the opposite. Then it looks fine. If we tilt the object, looking at it from the top, you'll see that it's actually very noisy. It's just the viewpoint that is beneficial here. Whereas after some iterations, they've been corrected. They are still very close to horizontal, so we have a lot of noise there. They are hard to, but the Kalman filter ensures that the noise sort of cancels out, and that they end up on the same line almost. Also gets more complete. Also, we can do some statistics. Having the ground truth, we can compute the position error of the accumulated primitives. So this is after the first frame. The upper row is accumulated representation. The lower is the stereo extraction. So what we actually observed in one frame. And in the beginning, it's of course the same. And then after 7 frames, you see that this is still distributed, and there are some with a very high error. In our accumulated representation, there are no with high error, and they are sort of moving towards very small error in position. After 14 frames, yeah, the tendency is the same. Yep, this one I actually already showed you, but that's just accumulation of physical objects. You get a more complete model that could use for different things. You see, the gripper of the robot is still part of our model, but we know the geometry of the gripper, so we could remove that afterwards as a post-processing step. Just removing every feature that belongs to the robot gripper. This shows the confidence of the features in the representation. So we see there's this characteristic 3-modal distribution. So this is after one frame. We have done an update. These are the newly added ones. So you see that's the 20% chance of a correct match. You see a lot of them is actually already have had a very good match. So they have high confidence now. And some of them have a very poor match. So they are about to be discarded. And as we progresses, they sort of accumulate here, and that will be our robust or reliable model. So we just need to threshold somewhere, and then we get the reliable features. There's of course some challenges in this framework. It's not trivial to do this matching on such a local level. I've listed some issues here that we are currently working on. You see, it's still not perfect. There's really room for improvement still in this object. We would like a more robust texture appearance descriptor to be able to match more powerful matching. Could be based on gap filtering. We would like to have a weighting between appearance and geometry. Today we only weight with the uncertainty, but sometimes appearance is more robust. But if, for example, a line is moving, if we move an object from one background to another, then the line will completely change appearance. So there we have to rely on geometry. So that's also an issue. How do we match when appearance changes like that over time? Then we have a problem with when we estimate the motion, our frozen features might not converge or stay at the, as it's a very local feature, it might diverge away from the object. We have no global constraint that keeps features together.
So if you are taking images of two objects at once, are you able to track both orientation of both objects? Or
no, not in this framework. Only one rigid body motion per frame, as it is right now. You could run it twice on the representation and see what fits which. But yeah, as a framework, only one rigid body motion. Of course, it can change after each, but you're right. Only. Yes. And finally, if there's any questions, just one. Yeah.
So in your features,
yes,
you also use color as a parameter between your, for example, your edge patches. So what do you take any measures in ensuring that you get a reliable color information from your camera, or is it only in certain lightnings and certain?
So when we weigh the color information in the matching, we assume that it won't change too much between iterations. I think that's a fair assumption as well, because usually images come pretty in a live stream, maybe a couple of frames per second. So we assume that
a lot can happen with color temperature in a second.
That's right. But then we would have to do some matching on different parameters, or color calibrate. We've been working on doing some color calibration where we have some color templates in the frame.
So you showed that it has been used for a project where it takes images out from inside a car
yes.
on the road. So I would imagine that in that scene you would see a lot of color changes.
Yes, but I'm not sure we used accumulation in that scene.
No, I'm just
okay.
actually just the features
No, but
of these patches of images.
yeah, but I think you're actually right. But the framework is so slow that it does not make sense to accumulate while driving, for instance, and use that as a. But you can record images and then run it afterwards, like a SLAM approach. Then it would build up a model of the surroundings. And there you're right.
So I just forgot that you don't use images after each other in the other application.
Yeah. Okay.
Yeah,
For expecting. Yeah. Then I brought this image. I don't know if you can see it, but there's a little plant here and another small. Is that right? Small one here. What's that?
Should be.
So there's two, right? Should be this one. Okay, so there's actually one.
The rest is
Soil or something. Where I try to apply our 2D feature line extraction. And it looks like this. And now you can't really distinguish the different lines here. I even can't. But that's okay. I chose some parameters, and these are the lines that came out. So, and if we put them together, link them together, so going a step up in the hierarchy of visual information, then you see, okay, these are the lines that we could detect. I'm a bit disappointed that I did not find sort of the growth point, which is so important. For some reason, there's nothing here.
But you only use the RGB images.
That was the RGB. I also have this is the near infrared. And also there, I had difficulties to find a threshold. Yeah, that was late yesterday evening, so this is from the near infrared. And again, you see there's not anything here. But that's probably a parameter question. I think it is visible, so. The reason I don't show you any 3D or stereo results is that I should have brought a right camera image. The difference in disparity is so big that the stuff is moving relative to each other between the different frames. So we would need to move the camera less for us to do reliable matching. Here it's not possible to get a good 3D reconstruction for us. And you tested dense mechanisms and had problems as well, I think.
Yeah, that didn't work out either.
Yeah. I didn't have time to that yet, but yes. That's actually it. That's what I have.